Welcome everybody. We're happy to have some of the Sudan from Harvard visiting. I'm going to introduce. We'll be talking on work with known friends and suspects on local correction of linear functions on the Boolean table.
Okay, thanks for everybody for being here. So this is, and I think I seem to be coming here every once in a while and have to find something new to talk about. So this is the topic for today. Joint work with Prashant, who's a student at Harvard, and Shrikant and Manasvi and Amit, who are all various parts of Denmark. So very quickly, I'll just launch into the problem definition and the results, and then let's a little bit. I mean, I want to have very deep motivation for this question. It's just that it's a natural question, so I'll hopefully be able to convince you that it's a simple question, and we should look for the best answers we can find. And so, what's the question? So you're given some oracle access to some function. It's an algebraic function, is what we're thinking of it as. It's a function from on n variables. Each variable takes values in some set S, and its value is some field element. And we are given some point in the domain called A, and we want to compute the value of the nearest polynomial at A. Okay, and nearest polynomial is defined as, so that we have the notion of distance between the functions, which is the usual one, the fraction of points on which two functions disagree is the distance between them. And P is going to be, in our case, the unique polynomial whose distance is at most 1/4, let's say, from this function. So on probability that the polynomial disagrees from this thing is at most 1/4. We are going to be looking at degree 1 polynomials today. You could ask the question more generally, but that's all we will be looking at today. And the way we want to do this is by, the way we don't want to do it is by asking for the value of f everywhere. We want to ask for its value in very few places, as few as possible, and we'll try to get to the result will tell you what kind of behavior we can get. So this is what is called the local correction of linear functions. That's what we're doing. In the talk, I will only consider the case where this domain S is just the set 0 and 1, and that's where you get the other word in the title, which is the Boolean cube. So you're locally decoding linear functions over the Boolean cube, and we just want the value of this function at any given point. Okay. Later in the talk, I will also talk about the more general version of the question, which will say, okay, suppose the distance is more than 1/4, can you find the polynomial? Polynomial may not be unique, but we will say, okay, find me a list of polynomials. And now it's a problem that's called local list correction. I don't have enough time, and hopefully will not have enough queries to find the values of all the coefficients. There are n coefficients, at least in a linear function. We don't want to make that many queries into the function value. We will be making much less than n queries. So we would say, well, okay, but I will be able to tell you the value of the linear function anywhere. But that's not very interesting if at different points I'm giving you values of different linear functions. So what we really want to do is to come up with L different oracles, if there are L different functions, each one of which faithfully computes a linear function, and all nearby linear functions are included in this list of oracles. So that's local list correction. We'll talk about both of these questions. For the second part of this talk, mostly I will be talking about not even the local part, just how list correctable is this function. All right, so that's the questions. Let me just state the results. The results are fairly clean and essentially in various ways the best possible. What we will get is a local corrector, which means we will compute the value of this polynomial at any given point, provided the distance is at most 1/4. Of course, sorry, again, stressing, we are only going to look at the case where the points input values are in 0, 1 to the n. And the field will be arbitrary and can be even.
Why can't you take the random value?
Good. So because I'm looking at the set 0, 1 to the n, and the field is possibly big, maybe think reals, a random line will not really even find a second point in the cube. Okay. If you're deliberate and take a second point, but then it will not be very a very random line. Great. So, I mean, so you need at
For
least,
larger field,
sorry?
it would work for larger field.
So it will work for, the field is a problem being large. It would have worked for larger domains maybe, but even with larger domains, it's kind of hard to get,
Wait, I thought I asked that for, what is the difference between S and?
good. So let's go back to this thing. This is, so we are given a function, the domain of it is just s to the n.
I see.
And so think functions of the Boolean cube,
Yeah.
but their real value.
My question is, will it work for larger S?
Larger S, there's some hope that if you take a slightly larger S, that something better might happen, but actually we don't know. And there's a very interesting question hanging around that. So if you could somehow use a larger S to do interesting things, that would be a pretty interesting statement.
So we are also asking for more.
Sorry?
When S is large, are we asking for more?
It's unclear. It's an incomparable question. You have access to the function at more places, but you also want to provide access to the function at more places. If the field itself is finite and this set is finite, then this set is equal to the field, then we are in great shape and we can do what we're going to just pick a random line and we can reconstruct the linear function on the line. And that gives us, and if the field is larger but constant size, then this is giving us a constant query way to recover the value of the polynomial everywhere. We don't have constant query methods to do this over the reals, for example.
Another attempt, why can't I take 2 points at X or to A?
Why can't you take 2 points at x or to a? Because I also have the affine, so the function is not, so it's summation ai xi plus a0. It will fail to give me a0 and basically that's already turning out to be a killer. That's not the only problem. I think there's some other problem that I'm missing at the moment.
For arbitrary S, there may not be two split points.
Right. So
For 0 on
the XOR is not good enough for us. Yeah, you want the arithmetic to represent the to be the field arithmetic. If it's just XOR, you can't use these two values to reconstruct the value of the function. Good. That's the correct answer. Great. These are the questions that really motivate the question over here. Some standard things that we tend to do are failing over here because this tiny set in the big field is just not giving us enough information to at least do many of the obvious things. We'll see what are the other options.
Why must such a linear function always exist?
No, that's what we're promising. So the linear function is promised to exist. So there may not exist any such function. Okay, any other questions? Okay, so quickly again the results. So we will get a local corrector, it will compute anything. If the error is less than 1/4, 1/4 minus epsilon, then the amount of queries that we're going to make is logarithmic in n. It's much less than n, which is good. We're not, n is not trivial either, but n is may have been trivial for certain codes and so on. So that's not the most, n would have been kind of an uninteresting answer. Log n is kind of non-trivial, and this is the first interesting result in a certain direction. Let me mention it in a moment.
So when f is equal to 0, 1, there even the log n goes away. It's because
when the function, the field is
field is 0, 1.
Yeah, is 0, 1, then this would be the Hadamard decoding problem.
So is there is this log n actually a function of how small s is in terms size of f, or?
That's a good question. What I know is that for larger fields, we do need the log n.
Okay.
Or something roughly logarithmic, not like divided by polylog factors and polylog factors. I don't know that it is needed for sets of size 3 or 5 or something. I don't want to make any bets on that at the moment. So it's a good question. For small fields, this may be there may be better answers. But certainly when the field gets large enough, this is even necessary as a lower bound. But for example, sorry, I do know the answer. In fact, if the field is small, we do, I think in the paper with Madhu and Srinivasan, we showed that there is a constant query local recorder.
Okay.
Uh, But that's I'm remembering from memory, and I'm not totally sure that I got that answer right. So small fields might work out. Constant size fields, constant characteristic fields, things are okay. It's when the field is of large characteristic, then the log n becomes necessary. A second theorem is a purely combinatorial theorem. We will say that the number of polynomials that can have agreement at most half minus epsilon. So notice that the set of linear functions, any two linear functions cannot agree on more than half the points. This is the famous Schwarzschild lemma or whatever. So we can go almost all the way to half, and half minus any arbitrarily small epsilon. With the number of polynomials that will be that close to a function is at most a polynomial in 1 over epsilon. It's a constant in 1 over epsilon, and that's already something that was not known. And then we sort of follow further and said we can actually recover all of these polynomials locally using roughly the same number of queries as before, logarithmic in it. So that's the second result. Most of the talk will be about theorems 1 and 2 and their questions.
The second doesn't follow from the Johnson bound, right?
The second will not follow from the Johnson bound because we are working over a large alphabet.
Okay.
And the code has distance only 1/2. The Johnson bound works great when if the alphabet is large and you are approaching distance which is best for this alphabet. And these are not codes which are approaching the rest of this alphabet.
So this distance looks closer to, it's almost the distance of the code itself.
Yeah.
So it's closer to capacity.
No, capacity is terrible in these codes, right? I mean, like saying the Hadamard code is not anywhere close to capacity.
It's half my epsilon or the half my square root epsilon and all.
So the amount that you're correcting is close to the distance of the code, which is good news. But you don't think of this as a great code. Just because
Three questions. Suppose we didn't care about locality. Is this always the second list code?
no, I mean, as far as we know, the list decoding bound was not known. So leave alone any
global.
I mean,
It's a combinatorial.
right, and consider given the fact that we can somehow prove a list decoding bound, saying that the number of solutions is small. If you just say, okay, find me all of them using time 2 to the n, what you have, I don't see an obvious solution. I mean, you might be able to set up other than the brute force solution, you sort of guess a set of points and hope they're all right. Okay, that's the best solution I can think of.
So something like Goldreich leaving will not work.
Something like Goldreich level will not work here again because of the same reasons. We are working over a very small domain, 0, 1 to the n, and the field is large. If the field was large and of characteristic 2, then maybe something like Goldreich level might have worked, but otherwise not. And the reason large field and Goldreich level, large field of characteristic 2 will be okay is because the arithmetic over F2 respects this other field. Great. So those are the results. So a little bit of context. I mean, it's not so much motivation. Just the motivation is this is a very clean question. So one explanation for why this is a clean question is that this is sort of coming from the classical Schwarzschild or etc. lemma, which says that if I look at the class of functions which are mapping s to the n to a field, they form a code whose distance, even when s is small and the distance degree d is a constant, it's a code of constant relative distance. So any two polynomials will disagree in constant fraction of the space, where by constant I mean something that does not depend on the number of variables. It can depend on the degree, but not the number of variables. In particular, degree 1 polynomials will all disagree in 1/2 of the places. So you have this very nice code sitting here. How many of these algorithmic results do we know about codes generalized to the setting? This question was asked in the non-local sense by a paper by Koparthi and Kim, and then they solved this problem sort of using algorithms which will explore the full domain. But now we want to do this locally and say, oh, look, we don't want to explore the full domain. We don't want to even make n queries. We want to make less than n queries. And when S, this domain equals the field size, then there are all these nice ideas like, take a linear line in the space, take a small linear subspace in the space, when a line is insufficient, all of those things work very nicely. But as soon as you look at the setting of S to the n, there are no subspaces sitting in here, and every sort of many of the nice ideas that we had previously stop working. So those are the reasons why we look at some of these questions. And a second context, this came from papers by Shubhangi and co-authors. I don't remember the exact set of papers over here. And they asked this question, are there locally correctible codes, the kind of codes that we're describing right now, whose alphabet is really the reals? So this is the exact setting that is included in our case. With the following feature, we don't care what the rate of the code is. The message length is something, so the number of coefficients of polynomials or whatever we are looking at should be some growing number. Its encoding can be as large as you want, but you should be able to correct a constant fraction of error, and we don't care what the constant is, just some positive constant fraction of errors. But the number of queries should be constant. And we don't know the answer to this question. So it's okay if your code takes n coefficients and represents them using 2 to the 2 to the 2 to the 2 to the n real numbers. As long as you can correct a constant fraction of errors with constant number of queries. Okay. So we just don't know this. Now, over finite fields, we have so many examples of nice codes that this kind of a question came as a bit of a surprise. And in fact, we were not angling towards this and then suddenly realized, oops, we have actually codes sitting on the reals. And for the first time, we have codes which are sublinear query complexity. It's not constant. We have not answered the question posed in the first bullet. But this is the first code which actually, makes number of queries which is less than the dimension of the code. A dimension of the code, somehow you can imagine somehow managing to get with some luck, but doing better than that is, seems. Okay. So this is the first such result that I'm aware of. So. All right, so with that, I'm going to start doing some algorithms.
And the code here is just taking linear functions, evaluating them on the grid.
And they're just for, and the field is of choice is the reals. Yeah. All right, so first thing I want to tell you is how to decode from a quarter of the errors, and I'll try to give you some of the ideas on how you build these algorithms, maybe not everything in the analysis. So we are starting with a function f, which is at a distance of 1/4 from some polynomial b. And what we will do is sort of progressively move towards this polynomial p by a sequence of functions. Each function will be a little bit closer to p. And sequence by sequence, I mean really a sequence of that length. There will be a function f1, then a function f2, and then will be a p. So what are the properties of f1? F is a distance about 1/4. F1 will be at a constant distance. The constant can be as small as you want. You specify the constant, and I will get that close to the function. In order to do that, F1 will be an oracle. I mean, look, at the end, what are we doing? We are trying to start with an oracle for the function f. We're trying to get an oracle for the function p. We won't get an oracle for the function p. We will get for a function which is reasonably close to p, agrees with p with whatever. If you gave me the constant was 1/100, well, at most 1/100 fraction of the points, we will disagree. Okay, so that's the kind of. So the first step is the constant.
F1 is with P is like at most down.
Yeah. Oh, I'm sorry. That's
Yeah.
right. That should have been an F1. Yeah.
Okay.
I can't correct it on the slide. There are a few other corrections that should appear on the slides, which won't happen today. Good. So, and the oracle for F1, we will allow you to make a constant number of queries into the oracle for F. So, from now on, we might as well sort of work with the setting where we say, oh, we have a function which is close enough. I will explain details of how to get these steps, but this is the outline plan. So, from now on, we can work with an oracle for F1 because I can simulate an oracle for F1 by making a few queries into F. Okay. The second step, another constant number of queries, actually not constant, poly, log, so something negligible in the total cost that we are willing to pay at the end. This oracle will get us to a pretty close approximation to f, but it will still not be exactly equal to f. Yeah. And it will have distance, 1 over polylog n. And then once we have 1 over polylog n, we will be able to go to p in one step. This is where we sort of lose the maximum cost. So it's omega. The number of queries is tilde of log n. So log n is log n factors. All right. So step
So
one.
tilde is both.
Sorry.
There's also rho tilde because of log n into log n. There's also another rho tilde sitting in step 3.
Yeah, that's right. So each query over here is going to take us that many queries into F1, which is going to take that many queries into F2. So the product of these three is the query complexity.
So here, what is tilde height again?
For any function, yeah. In general, tilde should hide factors which are logarithmic in the argument. And though there are people who use tilde of 1 to mean no, polylog n factors, not me. Okay. At least not today. All right. So step 1 is in some sense the most standard kind of a step. Or all we're going to do is, so we don't have too many options. So always the game over here is somehow we have a large number of variables. We want to reduce it to a question about a small number of variables. What can you do? In the general affine setting where we had, the domain was the fields, the vector space over the field itself, you could pick a constant dimensional subspace. And the constant dimensional subspace has only a constant number of variables, it's as much as its dimension. Now we can't do that. The only options we have are we can identify pairs of variables. Okay, I can just say, oh, look, this variable, that variable, we'll just assume they are the same. And that's what we are going to do. We are going to find a mapping which will take n variables and map it down to k variables. How? By just saying, okay, pick a random function h mapping the set n to the set k. The variable x sub I will be replaced with the variable y sub h of I. Okay, so now we have only k variables, y1 to yk. K is going to be a constant. So we have this big domain and variables, we reduce it to k variables by just identifying pairs of them. We will do one little flip, and this flip is happening outside this parenthesis. So what does it mean? If I want to contain, figure out what the value of the function is at some point A, I will XOR it, and here I don't care much about the algebra. The XOR is just a way to say x when I want to say x and 1 minus x when I want to say 1 minus x. So that's what's going on here. And if I do this and I take all y's to be 0, then I'm taking a XOR all 0. So that's one of the two to the k points that I'm considering in 2 to the n. The other 2 to the k points are obtained by choosing other values of y. So what I've done is in this box, sorry, where's the,
It should be chopped.
So in sort of this cube 0, 1 to the n of massive dimension, I've somehow decided to look at some subcube over here. I mean, I didn't know that the dimension doesn't shrink lengthwise, it's the number of variables that's really shrinking, but somehow I've reduced it. But this happens to be a random looking cube sitting over here. Okay, how random is this cube? It does pass through A. And so in the worst case choice of A, this is a pretty bad cube because 1 out of 2 to the k points that I'm looking at is completely determined. That's why what we will do is we will not analyze this step for what happens when you choose a worst case A. Notice that our goal is only to get a function which is usually equal to P of A. Not for all choices of A, but for random choice of A. For a uniformly random choice of A, this cube is a very good sample of almost pairwise independent set of points. Any one point marginally is clearly random. Why? Because A is itself random, it doesn't matter what I'm XORing it. if I take any 2 points, the first point is roughly as random as A. The second point is roughly as random as this one point. And if you take points in the middle level of this cubes, I have y1 to yk, but if I just even look at the middle level, I'm going to get a large number of pretty random points. So this cube that I'm looking at contains a pretty random sample of the overall space, and so has the right fraction of errors. The probability that that doesn't happen, where it has the right fraction of errors, the probability that doesn't happen will be something negligible as a function of k. As k goes to infinity, this probability will go to 0. That's the probability with which I will not be able to decode correctly. And otherwise, on the small subcube, I have to figure out which is the linear polynomial which agrees everywhere, and I don't have a local problem anymore because there's only 2 to the k points. I just look at all of them and find out what the best answer is. Okay, does this make sense?
What do you mean when you say it's negligible?
So it's little o sub k of 1. So the error is,
But is it exponentially small?
it's not going to be is it going to be exponentially small? I don't think so. Yeah, my guess is that it's going to be at most inverse polynomial in k. I mean, yeah, not totally sure. That's my best guess. No, actually, no, sorry. There are 2 to the k points that I'm sampling from the whole space. If this had been pairwise independent, I mean, if the second point had been independent of the first, then I should have expected that this would be like 1 over 2 to the k-ish good. Because it's not pairwise independent, but it's kind of okay, it's like 1 over some constant greater than 1 to the k. So it's exponentially small in k, but it's not going to be 1 over 2 to the k.
But then why can't I take k equals to polynomial get step to it?
Wait. Okay. Why didn't we do the number of queries is 2 to the k. I think the queries and the error are getting to be roughly the same at this stage. So we want to get to. So it's conceivable. Actually, I should check the calculations again. It's conceivable that if we wanted to get to polylog n queries, I could have used this either directly. No, directly won't work because I'll still get some error. So I will need a second step. It's conceivable that I could have gotten this step to get the error down to 1 over polylog n and then another thing. But right now, I think the best I can think of is the errors in the query complexity are polynomially related to each other. They are not exponential.
So think of the random walk is very strict. So if a k is equal to 1, for example, if the random walk is, it's like either at this point or to the diametrically opposite point. So it's a different graph.
Okay, good. So what happens? Sorry. Oh, yeah. If k equal to 1,
You're either at the point or at the diametrically opposite.
right. So actually, we are kind of usually careful in this case not only to we only look at subset of the points which are on this cube, on the subcube. Within the subcube, we will actually look at an error correcting code of points. And that's the ones that we'll actually use to reconstruct things.
So the graph will still be the.
It will still, yeah, and it will exploit the fact that we have large k. Yeah. Good.
What do you mean by the centers can brute force decode f to the c? Suppose I have 1/4 function. What does it mean to be? You're working over the reals, so what does it?
What does the brute force decoding mean? You guess this, which points are correct, which points are not in error.
Okay.
That's a constant size set that you're guessing out of a constant size set.
Solve a linear system.
And then you solve the linear system to find out what are the coefficients of the polynomial. Okay, good. So when you're working over infinite fields, brute force decoding should not mean enumerate all the code words. It is enumerate all the errors. And always there are 2 brute force algorithms for decoding codes, and only one of them works well in this case.
Sorry, how do you overcome the probability that the cube is not full?
That's some standard hypercontractivity of the cube or something. So yeah, I mean, I won't go into the details there. But
That depends on k, as in.
that depends on k. Yeah, it depends on k being large, and as k gets larger, it's like some
It's more than
this. Yeah,
H is a fixed function, right?
h is a random function.
Or H is a random.
H is going to be a random function, and
So
that's yeah. A is also random. So A and H are the two random things in this.
In the noisy hypercube, we are talking about A and H being random.
Right, yeah, yeah, exactly. So it's because in this, in step one and step two, because we only want to recover V of A for a random A. We want to say the probability of this whole thing failing is going to be small. We can afford to look at a random A.
So when the oracle right now is basically given a point A, the oracle is now going to pick a Y at random, so that the cube now contains A.
No.
Solve the problem at
Sorry, the oracle is going to pick an H at random.
yeah, sorry, H at random. The A is anyway, that's the
Right.
query I want to make.
Yeah, and in principle, now it's going to enumerate all the y1 to yk in this set and look at these values.
Figure out what is the
And over there, it will figure out what is the right subset of points to look at and what is the brute force decoding for this subset of points.
and answer that the oracle gives finally on what is the value at A is according to whatever is the best function.
Whichever is the best function that agrees with this, and
On that,
particular that function should be like a distance 1/4 minus epsilon over 2.
Okay.
What you started with. You were originally 1/4 minus epsilon, now you might be a little bit closer to 1/4. If you're beyond 1/4, then you want to answer this.
Okay.
And the error happens when the error is more than 1. Okay, so next step would have been step 2, but we're going to jump to step 3 first because it's a little cleaner to explain. And here it turns out that now we are actually, so what are we given? We're given a function which is like very, very, very close to the original polynomial. 1 over log n fraction of the values are wrong, but the rest of them are right. And now we want to get it right absolutely. So here what we will think about is the following. So roughly what's going to happen, you can draw a picture over here. Sorry, what's the everything? Yeah, okay. So now we should really draw the Boolean hypercube. This is the point 1 to the n, this is 0 to the n. So imagine you want to recover the value of the function p over here. Okay. So morally, it makes sense that if I could somehow make a bunch of queries in this level, and I will try to make log n queries over here, and try to reconstruct the value of the function at the top from these values in the middle. Okay. This should really solve the problem. If it's exactly at the middle level, you might say, oh, that's a little too dangerous, or maybe I'll corrupt the entire middle level. But you can do a little bit of perturbation from there on your own, pretty much. Okay, so but the real challenge is, how are you going to get a bunch of points over here to tell you about the value of the function all the way over there? And this is not going to be a large number of points. So it turns out after you do the right math and so on, you say, what do I want to call? I think I'm calling these points V1 to Vn, V1, V2, and to V log n. Okay. So there are a bunch of points in the middle. I want to make sure that when I can write summation alpha I Vi to be 1 to the n, where alpha i's are some integers, and summation alpha I is equal to 1. So alpha is a positive and negative, and they're doing some combination, they should be sum to this thing. Okay. If I can find some things that look like this, where the VI's are somewhere in the middle, then I'm actually done. Intuitively, this makes sense. You can formalize it fairly easily. I won't do the formalization. The question is, can you actually find points that look like this? And we give an explicit construction. I think this construction probably was the starting point of this paper, because this is something that Srikanth had observed when we were writing the paper with Vitali and like 10 years back, saying, oh, you cannot beat log n for this step. And when we proved that you cannot beat log n, we were trying to say, oh, maybe we cannot beat log squared, and also, but then we realized that there was a limitation to our negative result. And that turns out to be that thing. So how do you find a bunch of points that look like this? So it turns out, what do we want to look at? So let's say I write down these vectors v1 to vl, whatever it is over here. These are 0, 1 vectors. We are looking at points in 0, 1 to the n. Each column has roughly half zeros and half ones. That's what we want. On the other hand, when I want to multiply it by some vector alpha 1 to alpha n, I'm getting the all ones vector. And the question is, can you get this? So it turns out there is a very simple trick which does it. And the trick is the following: you use the following. So for a moment, pretend instead of writing down v1 to vl, I'm allowed, instead of 0, 1 vectors, I can write down vectors over the integers, any vector you want over the integers. What do you do? Well, it's pretty simple to get a vector like this. In the ith row, let me write down the vector I and I minus 1, just 2 columns. And I'm going to multiply it by 1 and 1. Okay, 1 and minus 1. So clearly, if I multiply this matrix, this vector with, into this matrix, I'm going to get 1. And these are integers I and I minus 1, everything works. But this is not the problem that we wanted to solve. Here I wanted to find these things are possibly large integers, and these are supposed to be zeros and ones. But I can simulate an integer I by writing it down in binary and using exponential size weights over here. So that's what I'm going to do. Instead of I, let's write down the.
No, I can't. I be the same for everything. You can just write 1, 0, everything.
I want, okay, good. I wanted the columns to have roughly equal number of zeros and ones. We didn't have that yet, but now we will require that constraint. So when I write down the binary representation of I and the binary representation of I minus 1, so these are just the bits of I and the bits of I minus 1. These are the vectors I'm going to write down. And here I will write down the appropriate linear combination. So multiply the first guy by 2 to the k, the next guy by 2 to the k minus 1, and so on up to 1, and then minus 2 to the k minus 2 to the k minus 1, etc. to minus 1. So if I multiply all of these, then I'm simulating the previous operation. And now I actually, if you look at all these vectors, I mean, the ith row has binary I and binary I minus 1. Every integer appears every column has an equal number of zeros and ones. This more or less does the trick. It may not after this we had to do a few more steps of manipulation, but this matrix does it. And you can see that this is where we're getting the logarithmic behavior. So there are log n coordinates over here in order to write down n numbers. Okay. So that's roughly what the proof of this step looks like. So that gives us, and okay, now what's the error correction? So we've just written down basically 1 to the n as summation alpha I v sub I. And if I want to find the value of the polynomial at 1 to the n, we will just write it as summation alpha I p of vi. And ignore the constant term for now, but this is roughly, that's the recurrent structure. So I don't have access to, I won't be at this point, I don't have access to p anywhere, but I can just replace this by f. And if you now see this in this hypercube, I mean, of course, all I got was these were some deterministic points sitting here, but I can permute the coordinates. If I permute the coordinates at random, this point moves to a random point in the space. So really, these are random points sitting in the whole cube. And the probability that f of vi does not equal to p of vi for one of these things is less than 1 over log n. I have only log n queries, so with high probability, none of them will be wrong. Now get the right answer.
Sorry, maybe I missed. Why is it important that summation alpha is 1?
The summation alpha equal to 1 helps. I think I need that for the constant term, because if I'm trying to reconstruct the function at, so the way I think of it is sorry.
You're right. You're writing the evaluation at the all ones point as a affine combination of the evaluation because the function is affine.
Yeah, it's because the function summation. So there is an alpha 0 term also. Or whatever. Sorry, there's a
A0 term.
Yeah, A0 term, which I think I know.
Okay.
Right. So that's as much as I wanted to say about this step, so I'll move on.
The login is necessary for this step, or even in general, I'm giving a function which is very close to a linear, like 1 over polylog log of 1 to this one, and I want to recover. Do we know that we need login queries there, or
So, yeah, I think so. Yeah. How close was the close? Yeah, I think so the lower bound usually comes by saying, okay, let me just corrupt every function. I will look at the hypercube that I had drawn there. I will want you to recover the value of the function at the top point. I will erase everything in the middle. And how few points can you combine in the middle in order to recover the top? And the answer is you need logarithmically many points, roughly log n over log n points to combine them to get that one. And now how much of the middle layer are you allowed to corrupt? I think all but an exponentially small fraction even. So like, yeah, at least you can get, yeah, very small amounts of error, not 1 over log n, but even 1 over poly n. Okay. All right, so moving to the more interesting things, the really interesting step I thought was the middle step, where we go from this function which is constant, as good a constant as you want, but it's only got constant error, to a function which has error, which is 1 over logarithmic in it. This step just iterates one basic operation many times. This basic operation, what we'll do is, in one step, you will go, oops, I'm sorry. Okay. So in one step, you will go from an error of whatever you had previously, so the square of what you had previously. So go from any error that you currently have to the new error, which is the square of that error. So if once you get this error down to a small enough constant to kill the whatever is the big O out there, then you're making progress, and now you'll be making rapid progress. And in order to do this, you will make one query, G2 will make one query to G1 and get this much closer. How is this done? Once again, we're going to pick one of these random cubes. And once again, we're going to say, oh, look, I want to recover the value of the function somewhere. I will not try to get the overall fraction of errors right, etc. I don't think I can afford to get that much. I will try to get all the queries right. Getting all the queries right doesn't seem like the right idea. The probability that I don't get all the queries right is at least the probability of one error, and one error is already the distance we're at. But we'll do this anyway. So here's what we're going to do. So I want to recover the value of the function here. I'll reduce it to some sort of constant dimensional cube that I'm looking at, where I'm looking at some extremal point. I'll look at the middle layer and only the points at Hamming distance 1 from this point. Okay, sum one point and all the points at Hamming distance 1. These contain enough information that if all these values were correct, I would be able to compute the value of the linear function on the entire cube. Okay, I mean this, I just need to recover all the k plus 1 coefficients in this k dimensional space. And these are all sitting in the middle, so these are kind of random looking relative to this point. So this is good news. But I need to get all of these values correct. This is only giving me one. I mean, so there's no chance that I'm squaring the error at this stage. So it turns out, okay, what we'll do is we'll repeat this idea 3 times and take the majority vote. Now, the way I'm going to get the wrong answer, if two of these trials get me the wrong answer, each trial is giving me the wrong answer with some probability gamma. Probability that there exist two that are giving me the wrong answer is gamma squared. And so that's where I'm getting this quadratic improvement, and this is all happening in a constant dimensional cube. And so constant number of queries squaring the error, and this gives me the.
You're going to pick 2 such balls.
Sorry?
You're going to pick 2 such
3 such balls and take the majority vote on the 3 opinions. in order to be wrong, I must have two of these values wrong. And that's where the word comes in. So the power is good, and now we're. Okay. So that completes the picture of the decoding for the 1/4 errors. So I should stop at 3. Okay, sounds good. So I'll give you a little bit of ideas about what happens in the half fraction errors. This is the most technically sort of intense part of the paper, but on the other hand, I mean, I think the algorithmic parts are the ones that sort of get most insight. So we've seen the parts that I understand the best anyway. Okay, so firstly, let me just remind you what the theorem is. We're saying, look, we're looking at a function f, which is mapping from 0, 1 to the n to a field. Actually, we will start looking at functions that map 0, 1 to the n to any group. You can always define functions which are mapping from integers to the n to any group, any abelian group. And that sort of, it's like a summation ai gi. Ai's are integers, so ai times gi is well defined. And summation of group elements is well defined. Yeah. So, and I've given some parameter epsilon. I want to know how many polynomials are there, linear polynomials. Excuse me, I'm sorry. That are a distance about half from this thing, little less than half minus epsilon. And these are like questions where we're sort of going beyond the Johnson bound, so trying to prove that the number of polynomials is small. Techniques get to be ad hoc, and we basically throw a kitchen sink of tools in this thing. Let me try to tell you all the steps that arise. First, we sort of reduce this thing and say actually there is a sort of step 0.0 before this, I think, which is to first say that, oh, look, no matter what, the number of answers that you're looking for is finite, where finite might depend on the group and the, sorry, not on the group, but on the number of variables n, and can be exponential in n, or something like that. In fact, I think we group W exponential in n. But why is that not obvious? Because you can't, just like Prahlad was saying, oh, what's brute force decoding? The field is infinite, the group is infinite. So you can't just enumerate all the possible linear functions and say, oh, that's the upper bound and the number of answers. Those are potentially infinite. But you can enumerate all the possible errors. And that does give you a finite upper bound. So once you've gone to sort of a finite number of possibilities, then you say, oh, look, the group itself does not have to be infinite. It can also be reduced to a finite case. And then finally you say, okay, look, now that you're looking at a finite abelian group, we have a very clean characterization of what they look like. Well, they look like, for our purposes, product of a 2 group and a 3 group with product of greater than equal to 5 group. So what's a P group? A P group is a set of elements whose are, P group is a group in which P divides the order of every element in the group. So all these elements which have sort of order 2 or a power of 2 fall in this G2, and then there are elements which have this other thing, and then we say, look, when you have a function that looks like this, well, it decomposes into 3 different functions. One which maps into the G2 part, one which maps into the G3 part, and one which maps into the G0 part. We will apply separately a decoding bound for each one, saying the number of possible functions is bounded, and then you just take the product of the 3 numbers, that's an upper bound and the less sums. For crude upper bound like polynomial and 1 over epsilon, the product of 3 polynomials is good enough. So this works. And we really are going to look at 3 cases, 2, 3, and the rest. In this case, I think the most interesting case was the G0 case. So we'll get to that, and then I'll tell you a little bit more. And there is an error in this slide that I noticed that it's not. So I'm looking at a bunch of functions which are close to some polynomial f. I should be looking at those that are actually that have agreement 1/4 minus little o of 1 from each other. What does a typical function look like over, say, let's think the group is the reals, okay? So you have, your function looks like summation ai xi, and for the time being, you might even think xi is a plus or minus 1 rather than 0 and 1. Your function is summation ai xi if you pick a random choice of xi's and plus minus 1, what's the chance that this function is going to be 0? Right? I mean, sounds like, oh, I should be able to apply things like anti-concentration and say, unless very few of the AIs are non-zero, every, almost, the probability that you get a 0 is like negligible. It's going to little over 1. The only exceptions are when it has sparse polynomials. They only depend on a few variables. So somehow the question goes from being a question about, oh, how can you get lots of polynomials that are, so typical pairs of polynomials are almost antipodal from each other. They are not agreeing on half the places, they are agreeing on almost one minus, they are agreeing on little over one of the places. So you want to take advantage of this fact, and then there's a whole collection of reductions. We sort of do a lot of things and say, well, look, first thing that you can do is sort of start looking at all of these polynomials and ask them how close are they to each other. You build a graph on these polynomials based on how close they are to each other. If they are very far from each other, they can't be mutually close to a function f. So that helps us. But there are some polynomials that can all be pairwise reasonably close. But the number of such polynomials is some absolute constant. So the number of polynomials that can agree with each other in 3/4 plus little of 1 or disagree from each other in that many places that are that far from each other is some constant depending on this 0.0001 or something. And once you have this kind of dilemma, you can basically say that, look, most of this space actually consists of polynomials that are actually close to each other in some senses. And if that's the case, then they all have to be sparse, and then you start analyzing what kind of sparsity can they have. It all be the only way you can get lots of different things is you have one polynomial depending on one variable, the other one depending on another variable, the other one depending on another variable, etc. They're all distinct variables. They're all distinct variables, then the chance that each one, when you pick a random value of a, the probability that they're agreeing is very, very small. So these are independent variables that are going to be with each other. So you can do some sort of a case analysis at this stage and deal with all of those. Okay, I see the signs coming in. So there's the G2 and the G3 cases. Let me say a couple of words about each one. G2 is the case of the groups having characteristic 2. This, was already covered by previous work because this is really Goldreich, Levin, etc., have done enough techniques this way that we could have handled this directly. Though actually in our proof, in our paper, we give a slightly different proof. The G3 case, we end up using two different tools. One, which is sort of some combination of this anti-concentration stuff that we did in the previous page, along with Fourier analysis to say, oh, look, at least for functions mapping to the group Z3, integers modulo 3, you don't have too many solutions. Once we had that, there is a different pack horse which uses the special intersection properties of these agreement sets, which we borrowed from some previous work with Dinur, Grigorescu, Koparty, and me. And we put them together and we were able to get sort of a list decoding bound in this case. And then once you have the G2, G3 cases, that will everything works out. So the number of cases over here is sort of immense. The neat thing is that the final answer is very compact. Any group you want, the list size is really polynomial and 1 over epsilon. That's it.
And the polynomial doesn't depend on the group.
The polynomial doesn't depend on the group, but it is an ugly and high polynomial. The groups are potential, principal, it could have the product of G sub P for all P. So I don't know, they're infinite and could have infinite things. So yeah, we can't afford that video. Okay, so this is some more slides on the thing. There's also the question about so let me stay on the thing. There's also this question about how do you do this algorithmically. It turns out for that there were enough techniques in the past that you had a nice algorithm, especially when you combine it with the previous parts. But there was some amount of more analysis that needed to be thrown in, and it's there in the paper. So those are the three theorems again. What are some directions? Some which we are exploring right now. So, yeah, I mean, but let me mention them anyway. There's a natural question, you know, what do you do when you have higher degree polynomials? Some of these steps generalize, but many of them don't. So it's like a kind of a delicate story over there. And also what happens when the set size is getting larger. A priori, it should be getting, you know, this was kind of a mistake that we made in the first paper with Bafna and Srinivasan, where we said, oh, look, we can do some analogous questions over the Boolean cube, and obviously it will work over larger domains. It's not so obvious at all. The larger domain sort of increases your challenges, it increases your access to the function. So it's incomparable, and so these works are looking at this. And general question that you might want to think about independent of these techniques is just, you know, can you get other locally correctable codes? Codes over the reals which have, say, dimension n for every integer n, but maybe you can make square root of log n queries or log n queries, etc. Are these possible or are these ruled out? We have not ruled out constant, and we are not getting anything. In fact, nothing better than n was known, and now we have log n, but one could imagine to a lot better. All right, thanks a lot.
Does that step generalize? The step you drew on the board where the value of the function at 1 was the sum of log and combination of log and that's for higher degree.
For higher degree, yes, there is an analogous step that we have been able to generalize. It's not in this paper, it's in some follow-up manuscript.
But this is as a statement something morally similar to this.
Something morally similar to it, so you're saying that every monomial can be reconstructed of degree d can be reconstructed by looking at a Hamming ball of radius d around the center. So, okay, in the paper we do already say that the Hamming ball of radius d captures all of these points, so that part is okay. I think we had some trouble not with this is what we needed in the step 2 of the proof. It's the step 3 of the proof that was giving us some problems, and that also. Yeah.
Go to the previous slide. So there's a login that is both in theorem 1 and theorem 3. Theorem 1, you already said that even for theorem 1, a login is necessary. Can you show that theorem 3 is actually the same login? In particular, instead of releasing a list of functions, I release a list of functions which are 1/4 close to this one. Can I then do it in constant query so that the login comes only from then doing theorem? You follow what I'm.
Yeah, and it makes sense, and I think that's what we do actually. So roughly, what I mean, how is the algorithm for theorem 3 obtained? You put in another, you know, f mapping to f half to f1, where f half is now 1/4 close to the thing, and for that we just basically say pick a large enough subcube of dimension 4 sub 1 over epsilon thing, and in that subcube you will actually be sampling the right number of points. So now you can do this decoding over here, and so you can sort of push, and then you can go f1 f1 half to f1 like in this paper, like in the proof that I gave you. We're still looking at constant queries, so you can get to something that is. If you want to get to within a constant distance, you can do it with a constant query. If you want the distance to be 0, that's when you need the log queries. Okay, thanks.
Madhu is in today and Thursday.
And Thursday, yeah.